David Academy, and we are looking at Fubinus Theorem. If you haven't subscribed to this channel, kindly subscribe and remember also to share with your friends. We are looking at Fubinus Theorem, and remember this is in David Academy. Okay, if we have a function of x and y which is continuous over a rectangular region R and with these dimensions, then this relationship is same. What will change is only the arrangement of dy and dx. Look here. That is for dy. If you want to start with the dy, that comes in sign like that. So what matters is the arrangement, and if you get a question which does not follow this arrangement, you will have first to rearrange. That's basically what Fubinus Theorem states. So the integral can be seen to represent a volume bounded by fx, the function of x and y on a rectangular R based on this relationship. So if you want to calculate any volume for a given region which is rectangular, then you have to apply the Fubinus Theorem. Now let's look at an example for this demonstration. If you are trying to calculate the area bounded by this function on this region, if you sketch this region, in Cartesian plane, and we have 0, 1, 0, 1, 0, negative 1, 0, negative 1, negative 1 is there, and we have 2, 1, 2, 1 here, 2, 1 there, 2, 1 there, and this one so it lies between negative 1 and 1, negative 1, negative 1 and 1. That is y-axis, in y-axis, and in x we have 0 to 2, so this is 2. So that's the region we are talking about. Yes, the region we are talking about. That's the region we are talking about, the rectangular region. And now we want to look to calculate the area that is bounded by this particular. Remember that's just an estimate of the way the function flows. It's not scale to scale. So this is 1 minus 6 x squared y. Okay. So this is basically an application of Fubinus Theorem. So what you need to do is that if we want to get the the area for this bounded region, we need to calculate or to have this operation dA, which is basically, remember here what matters is the arrangement. So this is 1 minus 6x squared y. Okay, our operation should, we can say we can use dx dy, can follow that dx followed by y dy. So that tells us that dx is the intervals for x, which is flowing from 0 to 2, then followed by y. Intervals for y is -1 to 1. So we'll start working first for dx. So if we integrate this in respect to x, we have -1, 1, okay, x, okay, 2x squared y, 2x cubed y, 2x cubed y, and this is from we are having this from flowing from 0 to 2, okay, x is 0 to 2 dy. So if you substitute the values of x here, you see we'll have -1 to 1, 2, and 8. So 2 take away 16y dy. Now next we integrate this in respect to y, so that now we having 2y minus, take away 8 8y squared. So it's learning from -1 to 1. So if you substitute this one, you'll see that we are getting -6 plus 10, which is basically 4. But remember, we are finding square the area of the bounded area bounded by this function. So this, of course, will be under square units. So that's basically the operation of Fubinus theorem. And what you need to note here is the operation on how which one follows the other. So the arrangement is the key. That's the only trick. Remember, if you have not understood any part, kindly leave a comment down there, and remember to hit the subscribe button to subscribe to this channel if you have not yet done so. Okay, let's look at a stronger form of Fubinus theorem. And this is now whereby we are involving functions. It can be functions of y, or integrating in terms of or the intervals given are functions. They are not straight lines. They are not straight lines. They are intervals. The intervals given are functions or curves. Generally curves. So it's called the one curves. So if you're having the area for this, then it can be described in this form. Remember, here we are using functions of x, functions of x. Those are two functions or two curves which are bordering the region, which are expressed in terms of x. But the next one is in terms of y. So these are half y's, piecewise in these the functions of y's. So the arrangement again matters. So this is in respect to dy, this one is in respect to dx. So this is the stronger form of Fubinus theorem. The relationship holds. It doesn't matter whether you are using the intervals, the constants, or you are using a function. With that, we can look at an example. And this is an example whereby we are given trying to find the surface area of the region bounded where A is the region bounded by a line. So here there is a line and is bounded by a parabola. So these two functions will help us to get the intervals, maybe in respect to y or in respect to x. Either way, we arrive to the same answer. So we can work out first. We try to express these functions in terms of x. In other words, I'm trying to take the first equation, which is this, and express this in terms of x. So it will be x being equal to y plus 1. Then I take the parabola also. I express this in terms of x equal to something, which if you look clearly at this, you see we have 2x being equal to y squared minus 6, which means x here will be same as y squared minus 6 to power half. To power half means it's a square root, not really. It means we need to divide. So we divide by 2 here, and we are having x being equal to y squared over 2 minus 3. So that's the true operation for that. If you have any comment on either procedure, kindly just leave a comment and we'll be able to look at it. If we really now want to get the intervals for y, because these are functions explain the same x, then we can equate them. And we'll say y plus 1 is same as y squared divided by 2, take away 3. So if you rearrange this equation, you are going to get what we normally call quadratic expression. And the quadratic expression, we can solve quadratic expression using the quadratic formula. And in my previous tutorial, I have looked on how to solve quadratic expressions. So you can look at the previous tutorial and remember to subscribe also, and you'll be able to see that this solution y will be equal to -2 and 4. So that's the interval for y. That means in our calculation, we need to get the double integral using Fubinus theorem of xy. The region is xy. We can say the arrangement follows dx dy. Remember, what matters is just the arrangement here. So for x is solution x. The first x is from y squared over 2 take away 3 2y plus 1. And the y's, the y's, we have solved for y's, and it is from negative 2 to 4. So if we solve this, of course, remember you have to integrate first from dx, like this, 4. So if you, in respect to x, you're having x squared over 2y from y squared over 2 minus 3 to y plus 1. Okay, so dy. Substitute back relevant, and then afterwards you do for integration or in respect to dy, and this will be, after substituting negative 2 and 4, you'll find that the solution is that 6 square units, and that basically is the solution for that. And that gives us a very interesting part, practice on stronger form of Fubinus theorem. If you have any question on how we arrive into this kind of answers, just leave a comment. I'll be able to note it down and be back to you. Remember to subscribe and also share with your friends. This is the Fika Academy.